Friends, welcome to lecture 57, in which we are going to learn more about the ice loads and ice spectrum. In the last lecture, we understood that crushing ice failure is considered to be the worst scenario, as this induces the maximum ice force on the member. Let us say, what would be the effect of ice on compliant platforms? In general, compliant platforms undergo harmonic oscillation under higher ice velocity. Under the crushing ice failure, three distinct ice force modes occur in the response. Okay. The main factor which governs this failure mode is ice velocity. So, the response of the structures under ice loads, especially under crushing ice failure, can be done by three methods. One, you can take this process as a quasi-static process. You can also handle this as a steady condition of loading. Further, you can also handle this as a phenomena of random vibration. So, Karna et al. In 2007 expressed the dynamic ice forced model. They studied the ice force effects on narrow and wide members. And they said that member response decreases with increase in diameter of the member, the study conducted by them postulated certain limitations of the study. One, this study is not suitable for intermittent ice crushing program. Two, it does not include nonlinear effects in the development. It also governs the approaches to estimate ice force. Let us quickly see what are various approaches to estimate ice forces. There are essentially four approaches. One is experimental studies on the scaled model. Now, this method uses scaling laws to examine. This method shows a very large disagreement when ice is modeled to the scaled value. That is especially in case of sea ice, because there is a large area but a very minimum thickness. So, the scaling law actually affects the correlation between the experimental studies and the ideal behavior in the numerical model. The second approach is using numerical studies. Numerical studies have a very serious limitation in terms of validation of results with respect to experiment. The serious limitation is validation of the study with experiments, which is quite a big challenge in the present scenario of research. The third approach, what generally people follow, is field studies, and the fourth one is addressed as data mining. In sense, one can examine the previously constructed platforms in the locations where ice loads are occurring. They are called ice infested areas. The second approach could be estimate ice loads through field measurements, not through the lab scale, not through the full numerical scale, but establish these measurements through field observations. There are many codes of practice available to estimate ice loads, like Canadian code, European, Norway, and USA. There are many international codes which help you to estimate ice forces. Out of all of them, an approximate approach, which is quite simple in frequency domain, is as below. the excitation force caused by ice is modeled as sinusoidal, pseudo excitation force. Subsequently, the response of the structure is characterized using the appropriate transfer function. Friends, literature has developed an ice spectrum for a narrow conical structure. In the absence of extensive field studies and experimental studies, one can use this ice spectrum to compute the loads on narrow conical structure. The ice spectrum S of f one-sided power spectrum inspection is given by A times f bar O square T bar minus del by f raised to the power r exponential of minus b by T bar alpha f to the power beta. Equation 1. Let us see what are the factors which govern this equation. Let us say A and B are called ice spectrum constants. A is 10 and B is 5.47 obtained from the experimental studies. So, A and B are known, okay. A is known, B is known. F bar naught is the force amplitude on the platform exerted by ice. So, F naught is also now known. F naught is given by an additional equation which is C sigma B h square d by LC raised to the power 0.34. We call this equation number 2. So, in this equation C is derived from experiments as 3.4. Okay, C is derived. Sigma B is called bending strength of ice, which is approximately equal to 0.7 megapascal. So, sigma B is known. H is the thickness of ice. So, H is known. D the diameter of the ice core. Okay, so D is known. LC is called characteristic length of ice. Which is further given by EH cube by 12G rho W to the power 0.25, call equation number 3. So, friends, in this equation, E is modulus of elasticity of ice or ice sheet, to be very specific, usually taken as 0.5 GPa, which comes to 0.5 into 10 power 9 Newton per mm square, so Newton per meter square. Okay. Of course, rho W in this equation, E is known, H is of course thickness of ice, rho W is density of sea water, which is 1025 kg per cubic meters. So, in this equation, if you carefully look at, of course, G is acceleration due to gravity, which is 9.81 meter per second square. So, we know G. So, we know LC. If you go back and check, we know LC. Okay. So, equation 2 all variables are described. Let us go back to equation 1. We still have something called T bar, is it not? That is not explained. Something called T bar. So, let us do that. T bar is called period of ice, which is given by LB by V, where LB is the breaking length of ice sheet and V is the velocity of ice sheet. Usually the breaking length is approximately 4 to 10 times of ice sheet thickness. Usually, okay, that is the usual practice. So, let us go back to this equation and see. I know now T bar. We will like to know the values of alpha, beta, del and gamma. So, let us see, alpha is 0.64, beta is also 0.64, gamma is 3.5 and del is 2.5 based on experiments. So, del, gamma, alpha, beta are known. Okay. So, this is a frequency f, which is a variable to be plotted. Let us quickly use the MATLAB program. Okay, to plot the spectrum. Equations are already given to you. Now, I will use the MATLAB program to plot the spectrum. So, this is the program being used for plotting ice spectrum. Okay. This was a joint effort made by a research scholar working under me. That is a program which is being written, available in my textbook. You can download and run the program in MATLAB. Let us run the program and see how typically an ice spectrum looks like. An ice spectrum looks like, as you see on the screen, which is having a very sharp peak at a very low frequency, and then it dies down instantaneously. So, it is a narrow band spectrum which is meant only for the Baha'i Gulf which is a typical input used for calculating ice loads on offshore platforms in Arctic region. Okay. So, the typical ice spectrum, so this is my F, this is my spectral density, which goes as high as 100, is an ice spectrum. For Bohai Gulf. The ice load which is calculated from the ice force spectrum is based on the field data. There are two major factors in the ice load. The first factor is the ice velocity. The second factor is the thickness of the ice sheet. Let us quickly see the probability density function of ice velocity and ice thickness. It is assumed that both follow Rayleigh distribution. And logarithmic distribution. Probability function of velocity v is given by v by 826.55 exponential minus v square by 1653.102. Equation 1a. Probability density function of thickness h is given by 1 by 0.55 h square root of 2 pi exponential of minus half natural logarithm of thickness minus 1.8671 by 0.5503 whole square. Okay, let me put the square carefully here. Okay, so one is a logarithmic distribution, other one is a Rayleigh distribution. Okay. Let us now quickly see what are the effects of ice load on offshore platforms. Platforms are generally designed to be ice resistant when they are commissioned in Arctic region. when commissioned in Arctic region. Ice loads are generally caused or ice loads induce ice induced vibrations. Further, ice induced vibrations will cause fatigue in tubular joints, it also causes lot of human discomfort to people on board. It also causes flange loosening of pipes. The effect of ice force on an offshore platform is generally measured from deck acceleration. So, while doing this analysis, it is assumed that the deck acceleration is a stationary process. It can be also taken as a Gaussian process, and it is a narrow banded process. Rayleigh distribution is used to determine the acceleration response of the deck. Okay. Now, the power density of the acceleration is given by A by sigma A square exponential minus A square by 2 sigma A square, equation 2, where sigma A square is given by the integral S u double dot power distribution of dF. S u double dot is called as the power spectral density function of the deck acceleration, which is developed due to ice loads on offshore platforms. If one knows the power spectral density function of the deck acceleration, then if the ice velocity is divided into j groups and ice thickness is divided into I groups, then the environmental parameters that govern the ice load can be defined by n cases where n will be I cross j cases, right. So, hence Pij shall give the occurrence of probability of kth ice case in working on the ice load. So, therefore, Hi comma Hi plus 1 comma Vj plus 1 is given by the probability of occurrence of specific ice case amongst the n cases. So, Pij specific case, if you want to look at, it will be integral Hi to I plus 1 Phh dH into integral Vj to Vj plus 1 PVV dV. Equation 3. So, we can also explain this using a flow chart. So, let us discuss a flow chart being used to assess the failure probability under ice loads. So, starting with the first factor, which deals with uncertainty of ice environment. Based on the uncertainty conditions and models, one can select the randomness of the parameters of ice load. What parameters are we looking at? If you remember, thickness and velocity, we are looking only at these two parameters. Okay. So, once we know these, we can then choose the failure probability of the platform deck. On the other hand, if we have variability in the performance of ice resistant design, our ice resistance platform, based on the variability, we can try to compute ice induced vibration characteristics. From the ice induced vibration characteristics, one can also assess the failure probability. Once the failure probability is assessed, then one can look at short term ice case under dynamic loads acting on the platform. One can also assess the failure probability of the platform itself directly. So, first we have to define a predetermined threshold value. Let us call this value as AL. Once this value is defined, then one can calculate the power spectral density function of the displacement under pseudo excitation. Which is SUU of F. Then one can define a specific case of ice. Let us call this the nth case. For the nth case, one can generate the ice spectrum, that is for a specific velocity and specific thickness. Okay? For a specific velocity and thickness, you can generate a spectrum which is Sk of F. This is for the kth ice case. Okay? Once this is generated, from this one can estimate the probability of occurrence of kth ice case, which is called as Pik. Once this is assessed, then one can compute the power spectral density function of acceleration response of the deck, which we call as SAA, K of F. Having computed this, one can further also compute the distribution parameter, which is sigma A square and K. Okay. We need to assume that a conditional exceedance occur. The conditional exceedance of probability of failure given kth case for the predetermined cases. So, under this assumption, one can now compute failure probability, which is at Pf, K. Further, if K is greater than, K is equal to N, then what happens? Okay. If K is equal to N, if it is not equal, then look for the nth ice case and say K is K plus 1 and run the program. If it is yes, then find the maximum of Pfk for K equals 1, 2 till N to obtain the failure probability based on short term ice case. Friends, ice load can be estimated by two methods. One, by failure probability approach, which we just now discussed the flow chart. Okay, this approach considers the probability of occurrence of failure event due to ice induced vibration. The second one is based on the expected loss in this method, or this method can account for failure probability and consequences due to ice induced vibration. We all know that ice loads can cause deck acceleration, it is accepted as a scenario of severe consequence of the ice load. Okay. So, the occurrence of probability of ice case Pik and condition of exceedance of this depends on ice thickness. So, very importantly, the occurrence of probability of ice case, which is Pik, and the condition of exceedance of probability of occurrence, which is Pfk, both depends on ice thickness. Ice velocity plays no role on the above. That is a very important factor which you must realize. When ice acts on the breaking ice cones, broken ice pieces are cleared up. Ice force is periodic in nature, which results in ice induced vibration. So, friends, we know that estimation of ice force has a basic assumption on a narrow conical structure. An ice is formed by breaking of ice. An ice force is a random process which is controlled by two parameters, thickness of ice and velocity of motion of ice plate. So, the ice force F of t can be given by summation of I equals 1 to n Fi t minus Ti or T dot I, sorry. Equation, okay, we will call it 3a, where in this above equation n is the length of the loading function. And T dot I is 0, whereas T1 0 is summation of j equals 1 to I equals 1, jj for I greater than 1, 3b. The function Fi t minus I, this function is the ice force model. For any chosen event of ice failure. How do you define this? The ice force model which is Fi of t is chosen for a specific event of ice failure. So, Fi of t is given by 6 F0I of t by Ti, F0 less than t less than Ti by 6. It is equal to 2 times Foi minus 6 times Foi of t by Ti, no, not into t, Foi into t is also into t for Ti by 6 less than t, Ti by 3. Otherwise, it is 0 for Ti by 3, t, Ti. We call this equation as 4. So, F0I for I equals 1, 2, etc. denotes the random ice force amplitude. Ti denotes the random ice force periods. Ice force amplitude and ice force periods are weak correlation. Okay? These two parameters have a very weak correlation, which are experimentally verified. So, they can be considered as an independent parameter in the model. So, variance of ice force is defined as expected value of f square of t minus expected square of f of t, equation 4b, where E denotes expected operator. Further, E expected value of f square of t is f naught bar square by 9, but sigma f bar square by 9. F bar 0 and sigma f naught bar are mean and variance of the force amplitude f naught. Hence, TFT is f bar square by 12 plus sigma f bar square by 9. That is, the standard deviation of ice force amplitude is about 0.4 times of the mean ice force amplitude. Is approximately 0.4 times of mean ice force amplitude. Okay, that is a correlation computed by Q et al. In the year 2000. So, therefore, the first moment is given by df of t is approximately 0.1 f bar square. So, friends, in this lecture, we learned how to compute ice spectra, how to handle ice as a random process which is controlled by the thickness and velocity of ice movement. We have also learned how to compute the ice spectrum or the ice load by characterizing this as a power spectral density function. Okay. So, kindly go through these lectures again and try to understand the parameters involved in ice load generation, which will be helpful for learning ice load as a process which excites force or load on an offshore platform constructed in Arctic region. Thank you very much and have a good day.